Okay, so in proving Gauss's law, we said if we had a solid region E like this, that I like to think of as the candy part of a Tootsie Pop, where the Tootsie's been removed, even though that makes me sad, okay? Then it basically has a boundary that comes in two parts. So we've got the outer boundary, the original surface S, and then this inner boundary, which is the boundary of this small sphere of radius A that basically surrounded where the Tootsie was before it got removed. Okay, and we said it seemed kind of reasonable, but maybe a little shady, to simply say that the boundary surface of E came in two parts. It was S and S sub A, and if I want it to be oriented away from E, that means the outer boundary has to be oriented out, as in away from the origin, and the inner boundary has to be out away from E, but in towards the origin. And I want to just justify that, and rather than attempting to draw lots of things, I've brought myself a model. Okay, so here, okay, this as a solid is E. It's hard to tell, but stuff's been removed from the middle. So this is an apple instead of a Tootsie Pop, but we're imagining that this is like the candy part of a Tootsie Pop. So the skin of the apple, that's my surface S. Okay. Now, I happen to have cut the apple into two pieces so that you can see, and it helps that I did this a little while ago so that it's starting to go bad. So this brown region, that's essentially my S sub A. That's the boundary of the inner part that I've removed. Okay. So E is the solid here that I have. It just comes in two parts. So this is the left part of E, and this is the right part of E. Okay. Now, what's kind of neat is that each one of these parts has a piecewise smooth boundary, but the piecewise smooth boundary is more like what we're used to seeing. It's not an inner and an outer boundary. It's all on the outside of the enclosed region. So I'm going to just focus on the right half right here. Okay. Notice that it has this skin part. Okay. That would basically just be the right half of S. It's also got this brown part right here. That's essentially the right half of S sub A. Okay. Now, I can see here that if I want those two parts to be oriented away from this right half of E, this solid apple, definitely this is going to be oriented out away from the apple, and this is going to be oriented out away from this part of the apple, which would be in towards the origin. Now, the boundary of this, though, isn't just half of S and half of S sub A, because there's also this piece of boundary right here. There's this portion of the plane that I got when I sliced things in half. So this is has a piecewise smooth boundary that comes in three pieces. The skin of the apple, which is just the right half of S, the brown part of the apple, which is the right half of S sub A, and then this portion of this plane. Now, if this is supposed to be oriented away from the enclosed region here is just the right half of E, here the normal would have to be oriented pointing leftward, because that would be away from the right half of the apple. Okay. So, working over the boundary of this, I get the right half of the apple, the right half of the inner sphere, but I also get this extra portion of plane, and that's oriented leftward. Now let's take a look at the left half of the apple. Okay, so now the solid that I have is the left half of E. It also has a piecewise smooth boundary. It has the skin of the apple, that's the left part of S. It has this brown part, that's the left part of S sub A, and it has this portion of the plane, which happens to be exactly the same plane that I got on the right side of the apple, because it's the exact same plane that I used to cut the apple into two pieces. So if I want the boundary surface of this to be oriented out, away from the left half of the apple, I definitely want the skin part to be oriented out. I want the brown part to be oriented away from this portion of the apple, which would be in towards the center of this little sphere. And I would want the plane part to be oriented away from this part of the apple, so it would be oriented to the left. So, if I integrate around the boundaries of these two things, okay, I know that the total enclosed solid is E, so that the integral I'm going to get is a total of 0, okay? But I know that that would be integrating over the boundary of this plus the boundary of this. That would be the right half of the skin oriented out, the right half of the brown part oriented in, and the plane oriented to the left. This would give me the right half of the skin oriented out, sorry, the left part of the skin oriented out, the left part of the brown part oriented in, and the same plane, but oriented rightward. If I integrate over the same plane, once with the normal vector pointing to the right, sorry, to the left, and once with the normal vector pointing to the right, those are going to cancel each other out. And so what I'm going to be left with is just the left and right halves of S oriented out, and the left and right halves of S sub A oriented in. Okay. So that notion that we could just say, oh, the boundary comes in two parts, away from E means out for the outer boundary and in for the inner boundary, it actually does work in the context of what we're used to, which is surfaces that just have a boundary on the outside. In order to get that, we just had to cut it into two such surfaces. And the extra surface, which is that plane, just cancels out. Kind of cool to see.